In the next section, we're going to be talking about elimination reactions, which are reactions to make carbon-carbon double bonds. Those types of compounds containing those bonds are called alkenes. So in this lecture, we'll talk about properties of alkenes, how we name them, and different isomers and their stabilities. So we haven't given you the full picture up to this point. Compounds with leaving groups, such as bromide, chloride, and iodide, can undergo two types of reactions with a strong base. We can have substitution reactions, which replaces the leaving group with a new group. We can also undergo elimination reactions, which gives us an alkene or a carbon-carbon double bond. That's what we're going to be talking about in the next section. Before we talk about those kinds of reactions, though, let's talk about alkenes and first how we name them. So it would make sense that instead of an alkane, like pentane, now we have an alkene, so we name it pentene. So for all alkenes, you're going to substitute the ane suffix for the ene suffix. Then what we're going to do is number the bonds in order to specify which two carbons share that double bond. So for example, we'll start, and we want always to give the alkene the lowest priority. So if we start here, we have 1, 2, 3, 4, 5, 5, 6. So this compound would be called 5, 5, 6 dash trimethyl. And the double bond is at the second carbon double bond. So dash 2 dash heptene. Notice that we didn't give the methyls the lowest priority because we want to make sure that the double bond is more important than the methyls, so you want to give that the lowest possible number if you're trying to decide. You might encounter some common names, but I'm not going to test you on those. Some that you might see are ethylene, which is just the simplest carbon-carbon double bond, propylene, which is 3 carbons, or styrene. And you've probably heard of polyethylene, polypropylene, and polystyrene, which are just polymers that are made from these compounds. Okay, so there's 4 different kinds of alkenes that I'd like you to be familiar with that differ essentially by the number of groups that are bonded to the carbon-carbon double bond. Hydrogen doesn't count. So if you have one group and 3 hydrogens, this is called a monosubstituted, disubstituted, trisubstituted, or tetrasubstituted alkene. So you just want to count the number of groups bonded to the carbon-carbon double bond to get a good idea of whether it's mono-substituted, di, tri, or tetra-substituted. And the substitution is going to help us determine stability and other properties of these kinds of compounds. Okay, so first let's talk about disubstituted alkenes. There's 2 kinds that you can have. Your 2 groups can be on the same side of the alkene. We call that cis substitution, or they can be on opposite sides of the alkene, and that's going to be called trans. So we would name this compound cis 2-butene. The carbon-carbon double bond is the second carbon-carbon bond, and the 2 groups are cis to one another, whereas this is trans 2-butene. Remember, these are diastereomers of one another because you can't rotate freely around this double bond. In order to rotate around the double bond, we would have to break the pi bond, which requires more energy than is available, at least at room temperature. Just to remind you, there's 2 kinds of cis-trans isomers that we've talked about. You can have 2 groups on the same side of the ring, so this would be cis 1,2-dimethyl cyclohexane, whereas this would be trans 1,2-dimethyl cyclohexane. Or you can have trans alkenes, where the 2 methyls are together on the same side of the alkene, or they're on opposite sides of the alkene. But if you have trisubstituted alkenes, we can't use the cis-trans terminology. We need to introduce a new kind of terminology, which we're going to call E and Z nomenclature. So in order to assign an E or a Z designation for these alkenes, you want to use the same rules for assigning priority that you did for RNS configuration. So split the alkene in half like this and assign these groups a priority based on atomic mass, going out one atom at a time until you get to the first point of difference. So for example, nitrogen has a higher atomic mass than hydrogen, so this gets priority 1 and this gets priority 2. And then you assign a 1-2 priority over here. So fluorine has a higher atomic mass than carbon, so fluorine gets priority 1, carbon gets priority 2. Notice that the two lower priorities are on the same side, and the two higher priorities are on the same side. The E and the Z stand for the German words. Entgegen means opposite, and zusammen means together. So these are together, so this is a Z alkene. Whereas over here, this is priority 1 and 2, and this is priority 1 and 2. So now the two highest priority substituents are on opposite sides, so this would be an E alkene. And this is going to be used for tri- and tetrasubstituted alkenes, this kind of terminology. Okay, so let's talk about the stabilities of different alkenes. What I want to start with is the disubstituted alkenes, which I think are the easiest to understand. So if you have the trans configuration or the cis configuration, the cis is going to be higher in energy or less stable. The reason is because those two methyl groups are locked in an eclipsing conformation. So you have two big groups that are close to one another, and they're repelling each other, but they can't twist away from one another like they can in an alkane. So the cis conformation is going to be higher in energy. If you have two choices, just cis and trans, you want to know cis is higher in energy or less stable. All right, so how do we know that? Well, we know that because we can burn cis-2-butene and trans-2-butene. When we burn cis-2-butene, it releases more energy, which means it was higher energy to begin with or more unstable. This is called combustion analysis. And this is how we're going to determine the stability of all the alkenes. So if we burn all these different isomers, what we notice is that this monosubstituted alkenes are the least stable, followed by disubstituted, then trisubstituted, and tetrasubstituted are the most stable. So this is kind of similar to carbocation stability. The more groups that you have bonded to your carbon-carbon double bond, the more stable it is. Just like the more groups you have bonded to your carbocation, the more stable it is. So tetrasubstituted will give off the least amount of energy on combustion analysis, and monosubstituted will give off the most energy. So to summarize, what I'd like you to know is that alkenes contain carbon-carbon double bonds, and we name them as alkenes instead of alkanes, so we change the suffix for these. The location of the alkene is assigned by numbering the bonds, the carbon-carbon bonds. So you want to count which bond actually is double bond. So you can have 1 pentene or 2 pentene. We can have monosubstituted, disubstituted, trisubstituted, or tetrasubstituted alkenes. We name disubstituted alkenes as cis-trans isomers, but we name trisubstituted and tetrasubstituted alkenes as E and Z isomers. So know the rules for assigning those priorities. And then in terms of alkene stability, I'd just like you to know that the more substituted the alkene is, the more stable it is. And that if you have two different disubstituted alkenes, the trans is going to be more stable than